I'm going to talk today about some work I did with Dennis Golesh of CCQ, sort of in the second half. And I think this was sort of a nice example of where we were able to pretty cleanly find this matrix compression structure in a physical application and use it to get very substantial efficiency gains. So I'm going to take you through that and try to give you an idea of what some basic fast algorithms based on this this hierarchical low rank compression structure look like. So the first half of the talk, I'll just talk about this type of matrix compression, and then in the second half, I'll get into the physical application. So just some general remarks. It's very common for matrices found throughout scientific computing to have some kind of structure that you can take advantage of to reduce the asymptotic complexity of storing them and doing various operations on them, as opposed to the price of dense matrix operations. So the simplest structure is just sparsity. Many entries of your matrix are 0. So here's sort of maybe a familiar matrix to some people. This is the second order finite difference matrix in 1D, which comes up in numerical PDE. So say you were solving a PDE by an iterative method, applying this matrix, if it's on a grid of n points, an n by n matrix would cost n squared if you did a dense application. But of course, only a few of the entries in this matrix are non-zero, so it's very straightforward to do an O of n apply. Okay, but the point here is that this is not the only kind of compression structure out there. There's many other types of compression to take advantage of. A famous example is the fast Fourier transform. This isn't always thought of as sort of a matrix compression technique, but this is an algorithm to apply the discrete Fourier transform matrix, and we use some recursive structure in that matrix to get an n log n apply instead of an n squared apply. So I'm going to talk about another very common structure, which is hierarchical low rank structure, and just starting with low rank matrices. So just some basic definitions. The rank of a matrix A is the number of linearly independent columns or rows. These are the same number. And that just means that all columns of A can be written as a linear combination of K of the columns, where K is the rank. So when we're on computers, we have to talk about epsilon rank, which is, loosely speaking, the number of linearly independent columns of your matrix to an accuracy epsilon. So without getting into specifics about norms, this just means that all of your columns can be written as a linear combination of K of them up to an error epsilon. So a numerically low rank matrix is a matrix with epsilon rank much, much smaller than the matrix dimension. And what's a simple thing you can do if you have a numerically low rank matrix to improve storage and let's say matrix vector products? So how can you compress a numerically low rank matrix? Well, the truncated SVD is one way. So in this first equality, I've just written the singular value decomposition. So UI and VI are n by 1 vectors, which are normalized, and the sigma i's are, so those are the singular vectors, and the sigma i's are the singular values, and they're written in decreasing order. So UI VI transpose is this outer product, and that's an n by n matrix. So what you've done here is you've written A as a sum of rank 1 matrices, UI VI transpose, which are in some sense written in order of decreasing importance. So if we have a matrix that we know has epsilon rank K, we can truncate the singular value decomposition like this. And now A is represented up to some error epsilon by this sum of K rank 1 matrices. So what does this do for us? Well, now we can recover all the entries of A, and all we need to do is store the singular vectors and singular values. So we have, 2 K vectors here to store and another K singular value. So we reduce the storage to O of n with a constant K. And the other thing is we can do fast matrix vector product. So we just apply VI transpose to a vector, that's a dot product, and then, multiply the result by sigma I UI and sum. So that reduces our work to Kn rather than n squared, okay? So I'm not going to sort of go into the cost of construction of the singular value decomposition. I'm just trying to, give basic ideas about this compressibility structure, and the rest is, involves many more details and is an active area of research for different situations. So let me try to give a physical example here. So this is the example of well-separated interacting charges from classical physics. So imagine that we have a bunch of so-called source charges with strength Qj at these source points indicated by the prime variables, and we want to calculate the electrostatic potential at a bunch of target points given here, okay? So Coulomb's law says that it's this. We just sum up the source charges divided by this Cartesian distance between the target points and the locations of the source charges. That gives us the potential at a particular target point. So if we have n source points and n target points, then computing the potential at all the target points is n squared work, because for each of n target points, we have to do this sum involving n terms, okay? So let's imagine now that the source points and the target points are fixed, and we keep getting new charge strengths here, okay? So what I want you to see is that this can be viewed as a matrix vector product, where the matrix entries are, 1 divided by this Cartesian distance. The rows are indexed by I, the columns by J. And so the question is, given some new charge strengths, can we calculate the potential due to those charges at all of the target points in faster than n squared, okay, n squared time, using some of these ideas? And I'm assuming that these charges are well separated. So I'm going to do a little MATLAB demo here. And so what am I going to do? I'm just going to put down 64 random source charges and 64 random target points in well-separated boxes, fix some epsilon for the epsilon rank, and compute the rank of this matrix here. So, okay, for 64 points, this is the picture we get. Here are the sources, here are the targets. This is what the matrix looks like. And we compute the epsilon rank, and it's 7, much less than 64. Okay, now in applications, we're really going to be interested in what happens when we take n very large. So let me start doubling the number of points. Okay, epsilon rank increased to 9. If I go to 256 points, we're still at 9. If I go to 512, still at 9. So this is a very nice thing. This means that, even if we take the number of points very large, the rank of this interaction is small, okay? And we can get major savings in matrix vector products just by, let's say, using the truncated SVD. So just to give an idea of physically why this is, if you think about one of the columns here, fix a J, that basically tells you what's the potential due to that source at all of these different target points. So if we take a nearby source charge, we go from this source charge to a nearby one, then those potentials are not going to change very much, okay? So there's some repeated information here. There's some savings to be had. And this is just saying that basically we could pick 9 of these source charges, and by taking superpositions of them with different weights, generate the potential due to every other source charge in this collection. That's, that's the concept of linear dependence. That's low rank. That's what's going on. Okay, so yes, we get an O of n algorithm using the truncated SVD. So let's make this one step more complicated. Now I'm going to consider the situation in which the target points and the source points are the same, okay? This is the so-called n-particle interaction problem. And I'm also going to regularize this Coulomb interaction by sticking this beta in, and that's sort of a technical detail which prevents singularities when a source point equals a target point, because if there were singularities here, I would need to kind of go to one level more complicated compression structure than I want to. But physically, you can sort of think of this as similar. So now these charges are no longer well separated. So the low rank before really relied on this separatedness. So we're going to use kind of a standard trick in fast algorithms and apply the previous idea hierarchically. So let me try to explain this. Just imagine a collection of particles on a line in 3D. And the point here is that if we consider the big matrix of all of these charges interacting with each other, that would be, that would be represented by this whole matrix. The targets are indexed by the rows, the sources by the columns. And this is in general going to be a full rank matrix. So what do? We split the interval in half. And now imagine that the left half are the target points and the right half are the source points. So that corresponds to these rows and these columns, or this block of the matrix. Now these charges have some separation. So we hope that this block is low epsilon rank. So now, and similarly, if we swap the targets and sources, we have this block, we hope that's low epsilon rank. So now let's look at just the points in the left half. So those guys interacting with themselves corresponds to this block, and that block is going to be presumably full rank. So let's split this panel in half. We get these two panels, and we can sort of apply the same logic. These guys as targets, these guys as sources corresponds to this block. And we hope that since these have some separation, we get this as a low rank matrix. Okay. And, we keep going. We continue this partition of the matrix down towards the diagonal until we have, a small constant number of particles per box. So if this works, we get what's called a hierarchical off-diagonal low-rank or Hodler matrix. And that just means that we make this partition and all of these blocks have epsilon, small epsilon rank, epsilon rank at most K. And then we could compute the truncated SVD of all the blocks. And when we count things up, we find that we have K n log n storage cost as opposed to n squared of storing this matrix. And if we want to apply this matrix to a vector, like computing this n particle interaction problem, you find that you've reduced a matrix vector product from n squared to also k n log n. Okay. And the idea here is that as the number of particles goes to infinity, we hope that this bound k on the epsilon rank is fixed for all of the blocks or is slowly growing, okay? And then we're gonna get our savings. So let me just do this second demo. And it's really just this experiment. I put a bunch of random point charges on a line, and then I'm gonna compute the ranks, the epsilon ranks with epsilon 10 to the minus 6 of all of these boxes, and I'll report the biggest one. Okay, so here are 64 particles on a line. Here's what this matrix looks like. It has indeed full rank, 64, but the maximum epsilon rank is only 8. And here the colors don't mean anything. I'm just showing you the blocks in this partition that I've constructed. So now let's go to 128 particles. Now we've increased the epsilon rank only to 10. Here's the partition. Let's keep doubling. Okay, they're random particles, so the epsilon rank went back down to 8. Let's try again. Okay, it's 10. Matrix is still full rank. Go to 512. We go to 11. Eventually, this will stabilize, and clearly we're getting a lot of compression here. So now I'm going to get into the physical applications. I should just say that, as I mentioned, building and storing the compressed representation is an issue, and this is a big field of research on how to do this well. There's some relation here between a big relationship here between what I've described and the fast multipole method, which you may have heard of. But the fast multipole method uses more analysis and less sort of generic linear algebra tools like the SVD, and it goes farther and actually has lower complexity, O of n. Okay, so I'm going to very briefly describe the physics here, and then I'll explain how we applied these concepts to our problem. So what is the kind of physical problem we're going to think about? We're talking about non-equilibrium dynamics of a quantum many-body system. So the picture you can have in your mind is we have a lattice of hydrogen atoms. You could think of a one-dimensional lattice. And the electrons can interact with each other and hop from one lattice site to another. And then this whole system is being driven by some applied field. Okay, so these are electrons, so it's a quantum system, and this electric field driving induces some kind of interesting out of equilibrium dynamics that we want to simulate. So as many of you know, solving the quantum many-body problem is exponentially hard. So you need some way of kind of making an approximation and getting around that. So here we focused on this Keldysh formalism, where roughly speaking, we write down an equation for some observables rather than the full wave function. And we're going to focus on this single particle 2-time Green's function. So this formula is probably unintelligible to most people, but what these Green's functions are some kind of correlation between, remember, we have electrons hopping from one lattice site to another. So this describes a correlation between a particle appearing at a site K at a time t prime and another particle disappearing from a site J at a time t. Okay, so these are the things that we're going to be solving for. And how this all works is that you write down some equations for these G's, and the G's interact via this kernel called the self-energy, which is typically written in some series expansion that's truncated at some order to avoid doing exponential work. Okay, so when the physicists come to me to work on this problem, this is what they put in front of me, a large set of scary looking equations, but we're not going to go into all of these. We're just going to focus on this kind of representative example. And so this is kind of an integral equation with its boundary condition. So let me rewrite that here. And I'm going to simplify it even more. But let's just kind of look at what the objects here are. We have these 2-time Green's functions and this interaction kernel. And so how this works is we kind of have an outer time stepping through t prime. So you could think of n points t prime. And then for each t prime, we have to solve some integral equation for all of these t's. Okay, so if we fix a t prime and do some manipulations, we get something that that looks like this. This is sort of a more standard form of what's called the Volterra integra differential equation. And let's just look at what this is. So it's like an ODE. We start with some initial data, some initial value, and we're going to step forward in time according to this differential equation. But what's special is at each time point, we have to compute this integral over the whole history that we've computed so far. So basically, the values of y that we've computed so far interact with the current y value via this kernel. Okay, so that means that we have to take n outer time steps. We have to take n time steps to solve each of these integral differential equations. And at each time step, we need to compute this history integral over up to n values. So that's n cubed work in total. And furthermore, we have to store the whole history of these g's and sigmas. So that's n squared storage, and that's a lot of work and a lot of storage. So that's what we want to reduce here. So right, this history integral here is the main object we want to focus on, and we're going to try to basically reduce the cost of computing it, and also reduce the cost of storing all of these objects. So if I just fix some time step Tn, we get this. And here I've just discretized this integral by some quadrature rule. So you have some quadrature weights going into the y. That's why you get y tilde. And what I want you to see first is just that you can think of the collection of all of these history integrals as a big triangular matrix vector product. So how do you see that? Well, if you fix some time Tn, you just have, this is just a dot product. You basically multiply this row by this column, the y's up to what you've computed so far, and that's this guy. And if you look at all of the n's at once, you have all of these dot products, and all of them only go up to the diagonal because you only want to sum over the history. So the collection of all these history sums is a big triangular matrix vector product. And of course, the problem is that we are only getting y coming in one entry at a time. So we can't just apply this big matrix all at once because we don't know the y values yet. We have to apply them one at a time. So how do we bring this back to the physics? What was our kind of empirical observation that enabled these accelerations? Well, we found that when we looked, these kernels sigma, which became these kernels k, have low rank off diagonal blocks a lot of the time for many different physical applications, as do the solutions GR. So here's a picture of one of the solutions. These kernels look very similar. And basically what we're going to do is just superimpose this Hodler structure on top of this and compress this matrix in this way. So I'm not kind of telling you how we build up that compressed representation. That's kind of another part of the algorithm, but we have an efficient method of building it. So I just kind of want you to assume that I have access of this compressed representation, meaning truncated SVDs of each of these blocks at every level of this hierarchy. So if we have this, how can we accelerate the evaluation of these history sums? So let me try to take you through this, and hopefully it isn't too confusing. So what are we doing? We're marching along, we're solving this integral differential equation and filling in these values of y. So at first, we just step forward as if there was no fast algorithm, as normal. So to compute these history integrals, we just do these rows times these guys and fill in these rows and go forward. Eventually, we've filled in enough of the y values that we can apply the first block in this Hodler decomposition. Okay, so these columns correspond to these rows. So now we have enough information to apply this block. And what does that get us? That gets us a contribution to a bunch of the history integrals corresponding to these rows. So we've sort of computed in advance the interaction between these values of y and history and some of the history integrals in the future. So now we continue our time stepping, and when we need to compute a history integral, we find that we've already computed most of it, and we just need to add in the part of the sum corresponding to these entries here and these entries here. Okay? And we go until we've filled in all of these guys, and now we can apply this block, and we get some contribution to all of these history integrals. Okay? And so you get the idea. Then basically at each time step, we take the part that we've already computed, and the part of the history integral that we've already computed, and we add to it just this kind of local piece. So when we do all the counting, we find that this reduces the cost of computing the history integrals to O of n per Volterra integral differential equation rather than n squared. So what did this get us in our application? basically we were able to, for systems that have this structure, which as far as we can tell are very common, we were able to reduce the overall computational complexity from n cubed to n squared log n, and the memory complexity from n squared to n log n. So we implemented this and tried it out on this Falokov-Kimball model, which basically is a simple model describing a bunch of conducting electrons interacting and hopping around with some fixed non-conducting electrons. So it's kind of like the system I told you to keep in your heads before. And so I have an implementation on my laptop, and so this n here basically tells you how long of a propagation time can you go to. So our goal here is to do simulations with an extremely long propagation time. And basically we were able to reduce a calculation that took 5 months to a day and 2.2 terabytes of memory to 4 gigabytes. So this kind of thing can really get you some savings. And for the physics people in the audience who are interested, we also confirmed this compressibility structure for a bunch of other systems, particularly a bunch of systems in the Hubbard model in these different regimes with different kind of driving protocols. Oh, and we have a full-scale general implementation on the way in this software package Nessie, with which my co-author Dennis is a developer of. So you'll be able to try this method out on your own applications. So just to wrap up, what are the general ideas which may be useful to you here? Number one is sparsity is not the only useful compressibility structure out there. I think, in this field, for example, there were attempts to reduce the cost of these history integrals just for systems where a lot of the entries of your matrices are 0, but there are many other compressibility structures and fast algorithms associated with them, and you can get big savings. So I talked about low rank and hierarchical low rank matrices, but it doesn't stop there. The FFT, as I said, is one example of kind of a compression of the DFT matrix, and there are applied mathematicians have been hard at work on compressing matrices coming from all different areas of computational physics and other applications. And I talked about storage and matrix vector products, but you can do lots of different linear algebra operations with these compressed representations, including inversion, solves. So that's it for me. Thanks very much.